you all are working on products and applications, natural-based materials. You know, one of the things you think back of is I got to see in Italy some work that being done with silk and biomaterials there. But at the end, you're talking about silkworms, and I don't know if we're going to plant a whole bunch of mulberry trees, right, to be able to do that. The industrialization of what you're doing is really critical, right? It's great to have the idea from a butterfly, but I was really intrigued by your comment, CC, when you said we know how to make tons of this now. Could you talk a little bit, the three of you, of scaling up some of these materials to actual industrialization and how that's done?
Yeah. Is this on? Don't turn it. Yeah, so I can go first.
Yeah.
So from a scaling perspective, like I said, we ran into some issues with scaling one type of material. We do view our material as a platform as well. And so to be able to figure out how to scale was very, very essential. So we constantly do techno-economic analysis. We worked with an outside contract manufacturer in chemistry so first we did laboratory scale production, figured out the procedures, and then had that scaled up to the next level in the lab, and then worked with the outside contractor to then get to the larger scale. And then use that as the way to understand, do we have any potential red flags from a manufacturing perspective? And the good news is that now with our current process, it is very achievable. We don't require any special containment, special systems. And you saw that in our case, we not only have to deal with material scale up, but also coating scale up. That's a whole different animal as well. And so we've had to work with other partners to scale that manufacturing. So once we have the material in powder form, then we figure out how to put it into a slurry. And then how do we then coat it onto a media that would be stable for usage in a filter kind of geometry. And so all of these, we have a lot of scale up challenges. But every step of the way, it starts with the lab. We do some proof of concept, make sure it works. Then we test with external labs, make sure that what we test in the lab is repeatable at the external lab using much more sophisticated and larger scale systems and instruments. And then we go to our partners to scale this process for production of material, for coating, for filter manufacturing. So every single step, it's a very iterative process of trial and error in-house, then going to external lab, and then for testing, and then with external partners to scale this for a number of parts of our process. So yeah, and our system also requires scale up. So it's prototyping many components. Started with our system started with a very I call it like a Tin Man type of look, very large, very mechanical. It was a very sophisticated to what we have now, which is well controlled with controllers and much better package. And we keep working on compacting the unit and making sure that it's tested to be feasible for production and ultimately for commercial sales. So it's a lot of different types of scale up.
Thank you. No, it's pretty similar. I would say that for us there are two key factors that played an important role. The first one is innovations in the manufacturing processes that are used for other type of products and applications. For instance, additive manufacturing, automated fiber placement for composite materials has been quite key to target some applications. So basically, that you need to be at the right place at the right time as well to be able to scale up these technologies. And the second one is partnerships. So work with the companies that have decades of experience in producing this type of materials and products, and try to transfer your knowledge and your ideas to them so that they can efficiently produce this at scale. That is also what allows us to work from aerospace down to sporting goods, because we do not produce. We wouldn't be capable of, producing for all these different applications. But we partner up with the tier 1 suppliers, raw material suppliers, to understand how to best scale up the technology for those products.
And Tiffany, NASA's big into partnering. You showed the aircraft fuselage there, and so to be able to go from a new composite material to scaling up and putting out, a new 737 to a day. What kind of partners does NASA have, and perhaps what mechanisms to do that, to commercialize materials?
Right. So there are a few paths. So most of the work that we do on my branch relates to, we develop materials at a lower technology readiness level. And so we really do rely on our technology transfer office to help us to make those connections that can work either through a Space Act agreement with a company or another institution. We can also license our technologies, and that can be another path. There are, in some other cases, where we are really keeping the work in-house. In the case of scaling up for a flight test article in space, it may make more sense for us to partner with another NASA center like Marshall Space Flight Center, one that specializes in flight test article development, to help us get to that next point and push the technology readiness level up of a various part. So.
Perhaps some questions from the audience?
Bam.
Hello, thanks panel. You guys are terrific. I have a question in particular for Dr. Mancatelli at Helicoid. I'm a biomimic and a biologist, and I'm really interested in that translation from biology to design, that abstraction of design lessons. And so it fascinated me to understand that in the application space, you're unable to mimic the low angle that an actual mantis shrimp uses in those layers, which is like 1 to 2 degrees of rotation within each layer of those chitin fibrils and fiber sheets. And so I'm curious about the R&D that goes into figuring out how close you need to be when, as you first translated that lesson, you were like, 1 to 2 degrees, maybe we can't do that in manufacturing. So can you talk about how you go from a design lesson in nature into a practical application in the real world?
Yeah, thank you for the question. That's straight to the point. Well, it's you've got to have a clear understanding of the engineering problem you're trying to solve. That's part of the tool set that you have available. So how stress redistributing these type of structures, how knowledge about fracture mechanics, of how damage evolves in these structures, and then it's a matter of applying that knowledge and understand how a certain performance relates, for instance, to the change in angle in the structure. So once you have that knowledge, you will find out that eventually by reducing that mismatch angle, you improve performance. So if you want, is like the way I see biomimicry for this type of applications is really an extra tool that you have available to solve a problem. Because our knowledge of how materials behave, structures behave is limited, right? If you want to run numerical simulations to know how composite materials would behave, you're 90% of the time you're going to get a wrong answer with respect to what you would observe experimentally. So we have a limited knowledge. You can use biomimicry to compensate that knowledge. If you had like a perfect numerical tool that simulates perfectly, and you could run an optimization, you would probably see a convergence to the solution you have observed in nature. So that's using the two and finding a solution that then is easy to communicate to the industry, and that at the end of the day is also commercially viable. So it has to save money, otherwise it's it's a no-go.
I have a question for perhaps all of you in some sense. When we are thinking about biomimicry and we are thinking about translation ideas to practice, we come up with this invention. You talk about Johann Eisenberg was one example, and helicoid is also a classical example out there. The challenges and pitfalls that you experience in terms of funding that allows you to kind of navigate from an idea generation in a lab and to all the scale up that you've been talking about. Can you share with us an experience of how you navigated some of that space and how you still do it, from taking a prototype from a lab scale to maybe a practice or even making a product out of it? Yeah.
Yeah, so for sure a fundamental role is what, like here in the US, for instance, federal agencies offer as a support to develop R&D and scale up and prove the concept, basically, because it's these are highly technical solutions that require a lot of R&D. Investors are not very happy when you want to spend most of the money to do R&D. So it's a fundamental support that is provided. Let's say that I would say 0.5% of our endeavors are supported through federal agencies grants, and allows us to to prove the concept in different applications and then find the right customers to bring it to market. So that's very important. The other important thing is trying to gather as much knowledge as possible of what has been done already in the literature, what has failed, what was successful, and trying to catalyze that into a tool that helps you to solve a problem. Yeah, I would say these are two big factors that plays a big role in the early stage.
So for us, and also based on a lot of my personal experience outside of Metalmar, I work with a lot of startups in materials and in tough tech. One of the problems is that companies run into this funding problem. And so you have a cool idea and can't quite seem to get the funding you need to get it off the ground. When it comes to tough tech, grants, in my opinion, just like what Lorenzo has already said, is a very, very important element of your funding strategy. So while it's exciting to look at startups that receive large amounts of VC funding, for the most part, when it comes to tough tech, climate tech, materials, it is really difficult to raise money from VCs. Your valuation is low, and your time frame to get to market tends to be much longer than the 10-year time frame that a VC fund has. And so you generally do have to look to some type of grant funding. And so we've benefited from quite a bit of federal funding, state level funding. Much of it we've used it for product-related R&D and scale up, and so that's been a major driver for how we come to this point. And the observation I mentioned earlier, where some of the startups that didn't try to get grant funding, they tried to bootstrap with their personal investment or angel funding. Oftentimes they cannot get through the laboratory phase just because it's so expensive. Just think like what we talk about, chemistry, materials, you need laboratory space. And in Massachusetts, it's really expensive to get laboratory space. And we're competing also with the biotech industry, where they can actually pay the high per square footage to lease space. And so it's really at a disadvantage for many materials companies, in my opinion. And so, looking outside of the typical type of thinking about, investor funding is really important. Another, obviously, if you can get partners to pay customers to pay for development. Another is, going into partnerships. Those are helpful, but do keep in mind that those take quite a long time to mature. Large companies move super slowly, and their time horizon is a mismatch in general with those of startups. And so you always need to have an option of how you're going to continue funding the company if you didn't get VC funding, if you didn't get partner funding and such. So, but be customer driven is ultimately the message.
And if I may add on that, it's we do sometimes, especially in the past years, played a bit with getting the customer to pay for the development project, but it's very risky because you are getting the customer involved in something that you are not 100% sure is going to perform how you want it. So if you do not deliver the results, then you lose the customer and you lose credibility. So it's it's a very hard, it's a kind of a chicken and egg type of problem.
In addition to that, another consideration is your IP. If you do decide to go with a customer-paid project or a partner-paid project, you oftentimes end up with a joint development agreement in which you have to specify who owns the IP that's generated. And so you have to be mindful about giving up your ownership of what gets developed through your effort.
Please.
One thing that I've seen at NASA is that it is very difficult funding bio-inspired research just because we actually fund any technology that can help us with our missions. And so one thing that I've noticed, and that's one of the reasons why I presented my talk in the way that I did, is that many on the outside are not fully aware of our technology challenges and the areas that biomimicry can play in those. And then internally, I've noticed that there is a lot of interest in biomimicry, but as engineers and systems engineers, we may not be aware of all of the potential. And so conferences like this, interactions similar to this, where there's an interdisciplinary group of experts, those can be very effective for us.
I was going to give you a shout out too with NASA as a major participant in the federal SBIR program, which I noted that you were both supported on. So that's a key way of getting that technology funded and that transition piece. We have a lot of hands. We'll take one more before the red light's already on there. So
I work with kids and learning about nature through systems like the pattern alphabet, which we developed. I feel like a lot of these things that you're talking about, these kinds of solutions, are things that kids can be thinking about with crafts in schools. And so I really wonder where the concept of crowdsourcing and contests has gone in terms of, like, we have this problem and, somebody can solve it, because it brings a lot of minds around the table that are very curious, very interested, and those are the people who are going to end up going into your industry. And I just see that the contest sort of format has really dropped, and I'm not sure why, but I feel it would be really applicable here.
Well, I think that the complexity of the problems we are trying to solve in everyday life becomes so high that the background of the people that are trying to solve those, it's really specialized, right? You find people that are extremely good at using Google Cloud and wouldn't know what to do with the Amazon Web Services, for instance. Although they are doing exactly the same thing, but they're just so used to use specific tools. They've built decades of careers on that, and then you lose a bit of flexibility of doing a kind of multidisciplinary type of thought process. So I would say that being able to stimulate that, since during the entire education, of an individual, it's fundamental, because using biomimicry and applying to engineering problems, for instance, or any other problem, it's effectively doing a kind of multidisciplinary type of activity where you need to look at something that you might know well. I'm not a biologist, I know zero, and trying to kind of abstract that information and translate it into something that is part of your world.
I actually think there are interesting contests. So I love hearing about what you're trying to do with kids, because kids are so flexible in how they think, and schools actually are moving towards this project-based learning across the country, and so there's a wonderful opportunity to take advantage of here, that using biomimicry as a platform to have kids get involved. So actually the Biomimicry Institute, of which Metalmark was a finalist a few years ago in their challenge, has a competition for kids in middle school and high school. And I'm hoping that, my kids' schools would start getting involved, because it allows them to learn about multiple segments of science, right, and bring that together, and then solving problems, right. We're trying to build young people into solvers of our current and future challenges. So why not start now? And so it's beyond that, there are other challenges I've seen, like with the DOE has a number of challenges related to direct capture of CO2. There are tons of them coming out all the time. The EPA has had challenges on wildfire smoke mitigation, and of which Metalmark was one of the winners. And so I think it's out there, and maybe it's not to say, hey, we have to have a competition for biomimicry, but all of these challenges are sort of problem driven, and it's up to the rest of us to figure out how we can apply biomimicry to solving those problems. I'm actually really excited to see that there are, in fact, a lot of challenges.
Right. And our Office of STEM Engagement regularly releases a call for competitions, like what you're talking about in centennial challenges. And we invite teams, of course, and if there is a bio-inspired solution that could help us address some of our challenges, like Sissy mentioned, that will be how you get that out there, because the same thing that we have at NASA, these are problem-driven.